Hello, and welcome to another edition of Physics Online, where today we're going to talk about projectiles. Let's first of all define what we mean by a projectile. It could be a football going through the air, or a baseball going through the air. It could be a satellite orbiting the Earth. Basically, a projectile is an object that is affected by a gravitational force. And in our analysis, we're going to ignore air resistance to simplify our equations that we're going to be using. So let's begin. Suppose the ball at the far left is released from rest. If we use V final equals V original, same thing as V initial, plus acceleration times time, then we can write an equation of motion for this ball. And the way we're going to do it is we're going to substitute for V final, we're going to put V sub y. In other words, this object is dropping downward, has a certain vertical velocity in the y direction, the downward y direction. And we can also substitute V sub o with Vy sub o. That's the initial velocity in the vertical direction, plus acceleration times time. So what is Vy sub o? Well, it's 0. We released it from rest. What is the acceleration? Well, the acceleration is due to that of gravity, and before we can put in this value, we need to define our reference system. Our reference system, in this case, we're going to make downward to be negative. It's our choice. I'm going to make downward to be negative, upward to be positive. So any vector going downward has a negative quantity. Therefore, what goes in this blank? We know the acceleration of gravity always acts downward toward the center of the Earth. So what's the sign and value for the acceleration of gravity here? And then we can simply write this equation for V sub y. So fill in these blanks right here, push that pause button, and then we'll return and compare answers. So here's what we come up with. As I said earlier, the original vertical velocity is 0. We're releasing it from rest. The acceleration, according to our reference system, is negative g, where g is 9.8 or 10 meters per second squared. And therefore, we can substitute these values in our equation and get Vy equals minus gt. This is the equation of motion for this object that's released from rest. And we can fill that in right in here. And note, when t equals 0, then V sub y equals 0, which is indeed the initial velocity of this object. And when t equals 1 second later, then the velocity is increased. 1 times g gives me around 10 meters per second, downwards in a negative direction. When 2 seconds pass, its velocity now has gone 2 times 10, or negative 20 meters per second. So indeed, it is moving faster because of this constant acceleration. Now let's continue. Now imagine a cannon fires a projectile, that is the cannonball, off a cliff. So here's my cannon, and here's my cannonball being fired off the cliff. It's being fired in the horizontal direction. That's why this is called horizontal projectile motion. The horizontal velocity vector, Vx sub 0, remains what? Since no forces act in the horizontal direction to change Vx sub 0. In other words, we're ignoring the effects of air resistance as this projectile moves through the air. So what goes in this blank? All right? And notice, as a hint, all the vectors have the same magnitude. They have the same length throughout. So push that pause button and fill in this. So we see that the horizontal velocity vector Vx remains constant since there are no forces acting in the horizontal direction. We're ignoring the effects of friction. So up here we can see that this vector is Vx sub 0. This is the initial velocity once this cannonball comes out of the cannon after being accelerated in the cannon barrel, and this remains constant throughout the entire motion. Let's continue. On the other hand, the vertical velocity component, what does it do? Does it increase or decrease? This cannonball is doing two independent motions. It's going horizontally, but it's also falling vertically. And it's falling vertically due to the accelerating force of what? What goes in this blank? At the instant the cannonball leaves the cannon, what's the value for Vy sub 0, the initial velocity? Okay? And what's the acceleration? And you should also be able to tell me what the equation is for Vy in this particular case here. So label this information on the diagram, push that pause button, and we'll come back in a few seconds. So we see that the vertical velocity component increases due to the accelerating force of gravity. At the instant the cannonball leaves the cannon, Vy sub 0 equals 0. That is, it has to come out of the cannon barrel momentarily, its vertical velocity is 0, and then it starts to increase in velocity due to the acceleration. The acceleration is again a equals minus g, that is minus 10 meters per second squared. And as you can see right here, the equation of motion downward for the vertical velocity is Vy equals minus gt. At t equals 0, then Vy sub 0 equals 0. In other words, this equation for the vertical velocity is the same as it was for the object released from rest, because we have two independent motions occurring here. That is, this object will fall downwards regardless of whether it has a horizontal velocity or not, and it will fall at this particular rate. Vy equals minus gt, Vy equals minus gt. And indeed, if there were no gravitational force to cause this object to fall, right, then it would continue, once it leaves the cannon, it would continue to move at a constant velocity in a straight line forever. Right? This is the nature of independent velocities. It has a velocity due to the force of the cannon accelerating it, and this object is going to move horizontally regardless of whether there's any gravitational force. If the Earth were to suddenly disappear, this object would continue moving. Now, what about the vertical displacement of the cannonball? We can find that by using our equation for displacement, x equals vit plus 1/2 at squared. We're going to change this equation to fit our situation, where instead of x, we're going to substitute y, because it's falling in the downward y direction. And instead of vi, we can substitute vy sub 0, the initial velocity of the ball. However, in this case, vy sub 0 is equal to 0. And so our equation now becomes, where again, recall that the acceleration due to gravity is minus g in this case. So fill in those blanks, and in addition, note that the cannonball is projected parallel to the ground, that is, it's going horizontally, and that follows the path of, well, what kind of path is this? What kind of path does this projectile travel? This path right in here. It's not linear. Push that pause button and fill in those blanks. So here's our equation. The vertical displacement of our cannonball can be expressed as Vy sub 0 times t minus 1/2 gt squared. But in our particular case, the vertical velocity and originally is equal to 0. And so when we substitute in for the acceleration, minus g, our equation for the vertical velocity becomes this, y equals minus 1/2 gt squared. And note that the cannonball is projected parallel to the ground and follows the path of a parabola. In fact, if we take this equation right here, you should recognize that this is the equation, a quadratic equation. And in fact, the graph of this quadratic equation is that of a parabola. And it's a parabola that opens downwards at the origin. So here's my parabola that opens downwards. And if we take a look at this, we can basically imagine only half the parabola really exists. In our case, there's no such thing as negative time. So this is the part of my parabola that we're talking about in terms of describing this motion of this object right here. Okay? And also, on your diagram, write down this vertical displacement, okay, from here to the ground. Write that as y equals minus 1/2 gt squared. And notice that that is the same as the vertical displacement for our object that we released from rest. They both have the same equation. Why? Because both of them started off with an initial velocity, Vy sub 0 of 0. Both are experiencing the gravitational force acting downwards and the acceleration g. So push that pause button and write this right on your diagram. So basically what we've done is label on the diagram that the vertical displacement for the ball that's released from rest and for the cannonball is the same. This means each ball will hit the ground at the same what? What goes in this blank? Push that pause button and fill in your answer. And your answer should be that each ball will hit the ground in the same period of time t. And the reason for this is, again, because each is falling the same vertical distance, each is undergoing the same acceleration due to gravity. And many students think that, well, if you take a look at the cannonball, it looks like it travels a longer path, and it looks like it would take a longer period of time to hit the ground as compared to an object that's simply released from rest and falls straight down. But this is not true. Basically, we're talking about no air resistance acting, and in each case, the only force acting is gravity, and in each case, each object is undergoing the same downward vertical velocity increase here, and the same vertical displacement. Independent motion is occurring here. It doesn't matter whether this object has a horizontal velocity or not. It's still going to fall with a constant acceleration and have the same vertical displacement for this cannonball as for this object released from rest. Now, what about the maximum horizontal displacement for our cannonball? In other words, yes, it's falling downwards, but it's also moving horizontally. And this maximum horizontal displacement is often called the range. Oftentimes you hear the phrase, well, the range for a particular missile is a certain value. That is, it's the total horizontal distance that a missile will travel while it's in the air. And this value for the range, it depends only on the horizontal velocity. So go back to your diagram and look at what we had as the expression for our horizontal velocity. It also depends on the total time it's in the air. The longer the object is in the air, then the greater will be this range, this horizontal displacement. So we're going to use our equation for x, okay? We'll stick with x because it's talking about the horizontal direction. We know what v sub I is and the time. We also know what the acceleration a is because recall, there's no forces acting in the horizontal direction. So what's the value for a? And therefore, our equation for the range or the horizontal displacement can be written. So see if you can figure that out and also label this on your diagram. Push that pause button and then we'll take a look at our answers. So our horizontal displacement only depends upon the horizontal velocity Vx sub O and the total time it's in the air. So we're going to substitute for V sub I, Vx sub O. We're going to substitute for a 0 because there is no acceleration in the horizontal direction because there's no forces acting in the horizontal direction. We're ignoring air resistance. So our equation simply becomes x equals Vx sub 0 times the total time that that object, the cannonball, is in the air. And if you go back and take a look at my diagram, this is what we're talking about. This right here is my particular here. This right here is my range, the total horizontal displacement for my projectile. And the equation is x equals Vx sub 0 times t total. So mark this on your diagram. Push that pause button, and then we'll return. Now let's look at an example. Suppose this cannonball is shot from the cannon with an initial velocity, original velocity Vx sub O is equal to 12 feet per second. Now since we're using English units, feet per second, then our acceleration, again it's downwards minus g, what should be the numerical value? It's not 9.8. What goes in this blank? And then what I'd like you to do is to calculate the horizontal displacement after 2 seconds have passed, and I've given you the answer here, and also calculate the vertical displacement after 2 seconds have passed. So push that pause button and get out your calculator, and we'll compare answers. So here's our solution. The value for g is 32 feet per second, and the direction for the acceleration is downward, so it's negative 32 feet per second squared for the acceleration. The horizontal displacement we found is x equals Vx sub 0 times t. The original velocity when it left the cannon was 12 feet per second. It traveled for 2 seconds, and so the horizontal displacement at the end of 2 seconds is 24 feet. For the vertical displacement, we use our equation for vertical displacement, noting that the original vertical velocity was 0, so this term disappears, so all we're left with is minus 1/2 gt squared. Substituting in minus 32, right, for this expression, minus, and then 32, we get negative 64 feet. and the negative sign tells us the direction. We're talking about going downwards in the negative direction. And if we take a look at our diagram, here's what we're talking about. There was a certain downward displacement, negative 64 feet, and there was a certain horizontal displacement, positive 24 feet. Of course, this is not drawn to scale, but you get the idea that there's both a vertical and a horizontal displacement at each point in time as this projectile describes this parabolic motion. So let's continue with these other problems. And so when you take a look at your worksheet and take a look at these other problems here, let's see, here we go. We have, suppose the cliff is 144 feet high. Calculate the time it takes for this projectile to hit the ground, and I've given you the answer there. And then we have another problem where we're going to calculate the range for this projectile. And then here's a problem, an example problem that allows you to take a look at an application, a real-life application of something like this. So push that pause button and fill in your solutions, and then we'll come back and take a look. So to get the time it takes to hit the ground, you will need to use this equation right here, where y now would be negative 144 feet because this object is going downwards in the negative direction. Solving for t, that'll allow you to get the total time it's in the air, the total time it takes to hit the ground. Don't forget to take the square root. Then to calculate the range, you will take this value for the total time you got here, multiply it times the horizontal velocity to get the range. And indeed, for this problem down here, you'll also need to use this equation first to get the total time is in the air. So that's it for horizontal projectile motion. I hope you learned some physics and have a good day.